All right, sorry, I just remember to start recording here. Okay, so that's our mass flow rate equation or our mass balance equation. And then I just wrote down here the reminders here. We had a couple different ways to write or express the mass flow rate. In particular, we had that the m dot could be written as the density times the volume flow rate, v dot, or using the fact that density is 1 over the specific volume, you could write it as this 1 over the specific volume times the volume flow rate, v dot. Or you could write the volume flow rate as long as you had like something of constant cross section, like a cylinder or a pipe. You could write that as, you could write v dot as an area times a velocity or magnitude of the velocity. So there are a lot of v's floating around here. So as usual, I try to be careful here. Lowercase v by itself is going to be specific volume. Capital V is extensive volume. And a lowercase v with a vector and a magnitude, we're talking about speed there. So just be really careful. You can't equivocate. You just got to watch the labels. All right. So do it in whatever way is really clear, because it's not hard unless you don't know what the letters mean, and then you're screwed. So just be careful. And then you have to watch the units on all those things too, right? This will be meters per second. This will be meters cubed per kilogram, and volume would be meters cubed. So V volume dot would be meters cubed per second. So you just got to watch the units on all those things. All right. Continuing with our review, our lightning review, the energy balance equation is doing what it sounds like it's doing. It's keeping track of the energies. So that's be the energy inside the control volume. But since we have mass in and mass out and things are changing in time, we don't really keep track of the total energy. We really keep track of the energy rate of change, the energy, the time derivative of the energy. And some of this is more or less, I think kind of intuitive here. You'd think, well, okay, you got this volume and maybe you've got a boiler or you got a fire underneath it. So you're adding heat, and then maybe you've got a propeller spinning. So you're extracting work. So you're going to have positive, so you're going to heat in is going to count as a gain for the energy in the control volume. Power delivered to a propeller would be a loss of energy in the control volume. That kind of makes sense. Q minus W. And then we also have inputs and outputs or exits, water in, water out, or sorry, flow in, flow out. So each flow in is going to count as a gain in energy for the control volume, and each exit is going to be accounted for with a loss of energy. So you get a minus sign. And then you'll notice here, we're using enthalpies all the time. Enthalpies. Can somebody tell me why we're using enthalpy and not internal energy there? What's the difference between enthalpy and internal energy? Okay, the difference between them is psst, the sound, right? The difference between enthalpy and internal energy is psst, that extra energy needed to make room for things. Well, since things are flowing through these systems, you're having to make room. As you push something, if you push mass into the system, then the energy that's relevant isn't just the energy of that volume of fluid, it's the energy of that volume of fluid plus the extra bit of energy needed to push it in. So you're always talking about enthalpies here for control volumes. So for control volumes, we will have enthalpy all the time, or frequently. I don't want to make a hard statement, but basically, yeah. All right, so enthalpy, enthalpy, enthalpy. All right, so we're going to say that the rate of change of energy inside this control volume, this region, is the heat rate minus the power delivered to some propeller or something. And then I also have the energy associated with the mass added minus the energy associated with the mass taken away. And you notice that each of those is an m dot times the intensive quantity. So the things in parentheses are intensive quantities. So these are, so you would call this specific enthalpy, specific kinetic energy, and specific potential energy. And all of the time dependence is concentrated in the m dots. These are just going to be constant fixed numbers for us. All the time dependence is concentrated in the m dots, which we will actually take to also be the constant rates when we talk about steady state here in just a second. So in particular, though, lowercase ke is the kinetic energy per unit mass, because it's the specific kinetic energy. And if you think about the formula for kinetic energy, you're going to lose the mass. So it's just 1/2 velocity squared. There's no mass there. Similarly, for potential energy, it'd be the extensive potential energy divided by the mass. So it'd be, if we're talking about gravity, it would be g times the height, gz. Z is the height of the pipe or something like that. For almost all of our examples, in fact, all of them that I can think of that we will work through, you can just ignore this. If you're digging a well, if you're talking about something that are, hundreds of meters deep or 1,000 feet deep, then you would have to worry about potential energy as well. For us, it's there, but numerically it is so small compared to everything else, we just don't care. Because remember, the enthalpy changes we're talking about here are usually in the, say, kilojoules or BTUs per kilogram. So these are large numbers, kilojoules. Whereas when you just plug in numbers, kinetic energy, that's going to come out in joules per kilogram. Whereas enthalpy is kilojoules per kilogram, and you have to get the units fixed, which means there's a factor of 1,000. In the metric system, there's a factor of 1,000. It's even worse. Well, not worse, but you have a more complicated conversion to do for barbaric units, BTUs and foot-pounds and stuff. And so that means that these kinetic energy terms typically are very suppressed. And then potential energy terms are even going to be numerically more suppressed. They're just going to come out smaller and smaller and smaller. So frequently you can ignore the kinetic and potential energies. It's not that they aren't there, but just numerically, if these come out in the few joules or even tens of joules, maybe even 100 joules, well, what do you care when it's sitting next to something which is in kilojoules, tens or hundreds of kilojoules? Well, then you don't care about these things typically, but sometimes you do. So you have to read the problem and know what assumptions you can make. But it comes up a lot. If you do keep these around, you have to do a unit conversion. So you have to be careful with units on these. We did an example. Do you remember doing the example the last one we did before Thanksgiving? There was some annoying factor of 1,000 unit conversion. That typically is there. If these kinetic and potential energies are important, you have to watch the units carefully. Again, none of these things is hard. It's a whole bunch of little things, little details to remember. Just got to remember it. Okay, steady state, which is what we will always assume for our problems. Steady state means that inside that volume, none of the properties are changing. So basically up here, when we had m dot for the control volume or the energy dot for the control volume, those are going to be 0. We're assuming, so that doesn't mean that nothing happens. It just means that you're balancing the inputs and outputs so that inside that volume, overall, nothing is changing. Okay. So for the mass flow rate, what that means is that you add up all the mass in, that has to equal all the mass out so that you don't get a pile up inside the volume. For the energy equation, you're just going to get 0. Is that you have to balance the heats in and the work out with all the changes of the fluid flow energies. So in practice, what we're talking about is we will study machines or systems which have settled down. So we're not really focused on the startup or slow down. We're not worried about what happens when you first plug in the refrigerator. We're going to assume that it's just sitting there running for a long time, or anything else, power plant or all that stuff. Those are the same things, right? Finally, we get one last simplification that I can state without specifying this real machine. For many of our devices, we just have one input and one output. Not all, there are a few, like the heat exchange is really one that comes to mind where you don't have this. But, so I'll write here. Works for, I'll make a list here. Sorry. I'll find the tool. Works for, so things with one input and one output. That'd be a nozzle or a diffuser, right? One in, one out. Oh. A turbine. A turbine. You could have a, what else could you have? You could have a boiler. Typically, we just have one line in, one line out. Same way with a condenser. Heat exchangers, sometimes, it depends on, are we exchanging it with the air, in which case we don't keep track of that, or if we have a heat exchanger with another line of fluid that we are controlling, then maybe we think of it as a single thing with many lines in and out. So we'll not have that. Condenser, though, usually just one. What else could we have? Well, we could have a pump, right? Pumps have one line in, one line out. Could have a compressor, same thing. One line in, one line out. We're squeezing it in the middle. I'm sure I'm missing one. What else do we use? I'll cheat here. Oh, throttle. Our throttling valves have one line in, one line out. That's basically it, except for maybe a heat exchanger. All of these things just have one line in and one line out. So if you think about it, if you go up here and apply that to the, if you have one line in, one line out, when you go up to the mass flow rate equation, you just have one, the sums are all trivial. There's just one input, one output. So that means everything, the inputs equal the outputs, because right, the equation says that the inputs add up to the, minus the outputs add up to 0, and you just have one of them. So the input is the output, and we're just going to call that m dot. We're not going to label in and out because they're all the same. That typically is what happens. So that's going to be our mass flow rate equation for one input and one output. Similarly, then, if you're running it in the energy equation in steady state, so you go back up here, it's steady state, so it equals 0. And then if all the m dots, first of all, I should edit this. This is wrong. I can make it a little simpler than what I've written. If you only have one input and one output, you wouldn't sum over the inputs and outputs because there's just one. Oops. A second. Computer a second here. I'm asking to do a whole bunch here with Zoom, and I'll get rid of that. Drag it in. There you go. So, look at this equation. If you don't have to sum over the inputs, there's just one, and all of the m dots are the same. It's just a constant coefficient. So you can divide everything by m dot, and you can write as 0 is equal to the heat flow rate, or sorry, yeah, divided by the mass flow rate Then you have the power delivered divided by the mass flow rate. And then over here, the nice thing about doing it this way is these terms in parentheses are all specific terms and they're just constants. So basically, the problem would just tell you the one of these or ask you to find one of these things. These aren't things you can look up, but everything else here you can either look up from the tables or, knowing a velocity, calculate very simply. All right, so this is kind of the final form of an equation without having to really specify too much to any particular device. All right, so let me pause there. It's kind of a summary of everything we did last time. Are there questions about what any of these things mean? Okay, because before we start doing examples, you've got to know what these things mean. Does anyone have any questions on that? Nobody's saying anything. Okay. All right. Abe says he's good. All right. So nozzle and diffuser, standard assumptions you can make. So kind of as far as a device, it looks like the way you're supposed to draw it is some sort of a trapezoid with a line in and a line out. If it's a nozzle, then it is narrowing during the flow. If it's a diffuser, it's going to widen during the flow. And I should have said that. What are standard assumptions by these? I should have said this. The standard for a nozzle, we can assume the velocity out is greater than that auto spell. Velocity out is greater than velocity in. And then if you think about it, just think back to Bernoulli's equation, or you can use the flow rate, the energy equation and think about enthalpies, but it's easier just to kind of intuit the answer from Bernoulli's equation. We know that if the velocity grows, the pressure drops. So that is going to mean the pressure out is going to tend to be less than the pressure in, just coming from Bernoulli's equation. Okay, so for a nozzle, you're pinching it down, decreasing the area, which increases the velocity using the mass flow rate equation. But if the velocity increases, the pressure drops. For a diffuser, then all of these things are reversed. So copy and just reverse these. Okay, for a diffuser, the area grows, which means the velocity drops. So velocity out is less than the velocity in. But if the velocity drops, then the pressure must increase. Again, intuiting that from Bernoulli's equation. All right? Is everybody clear on those assumptions? Similarly, if you have no work and you have no potential energy change, if you have there are no fan blades, nothing moving, you're not extracting work during this device. So there's no work or power delivered or anything like that. These things typically are small. And even if they're not, we think of them as large, they might be in a room, but you need changes in heights, which are, hundreds of meters to make potential energy typically very important. So don't worry about potential energy. And oftentimes, if you can insulate things, you can minimize the heat transfer. So oftentimes you can ignore heat transfer. Not always. Sometimes you can't make that assumption. So read the problem. If it asks for you to find the heat transfer, then you can't ignore it. But a lot of times you can do that. Similarly, in many situations, you're talking about slow velocities, in which case, even though the velocity changes numerically, it doesn't affect things very much. So you have to read the problem to figure that out. So anyways, when we write down for a nozzle, when we write down the flow rate equation, the energy balance equation, we're going to have 0 equals so we're going to be able to ignore work. Hold on, sorry. We're going to ignore the work. I'm just going to edit the equation here. And we're going to ignore potential energy. And we're left with, so we're going to have possibly heat, maybe, and possibly kinetic energy. And so we get this equation. All right. Best case scenario, we have no heat and we have no kinetic energy. And so we're just going to get that H in equals H out. So in that case, we would get enthalpy in is the enthalpy out. That's if you can ignore kinetic, ignore the heat, ignore potential and work at always. Then you just get that the enthalpy in is the enthalpy out. Now, that doesn't mean that nothing changes, because remember, enthalpy is internal energy plus P times V, specific volume. So what can happen is basically you can, let's think about that. What would happen if you keep the enthalpy the same on the way going through, but you increase the pressure? What would that do? What would that change about the system? Can someone call out what they think that might change in the system?
Would it be the velocity?
Oh, sorry. Can you say it again?
Would it be the velocity?
Okay, so if the velocity would change, but it changes, but not enough to, hold on a second here. One of my kids was snuck Minecraft on my computer. Couldn't figure out what that sound was. Sorry. We're all doing school at the same time. It's great. So if you're right, so the velocity would change. Now, it changes, but it's not enough to compare to the enthalpy. So that's why we would ignore it in kinetic energy. Okay, so velocity changes. What is the formula for enthalpy? Write it down here. Remember, enthalpy equals internal energy. When you see internal energy, think temperature, right? And other stuff, but temperature, it depends upon temperature, plus pressure times specific volume. Okay, so if the enthalpies are staying approximately constant, and you know, say for a nozzle, right? For a nozzle, what happens? The pressure drops. Sorry, for a nozzle, the velocity increases, the pressure drops. Okay, so for a nozzle, the pressure drops, but if you're keeping the enthalpy constant, you might be balancing that by increasing the internal energy. Okay, so you have a pressure drop and an increase in, to compensate, you would increase internal energy. But to do that, what do you expect that to maybe mean for temperature? What do you think? Yeah, increase, right? So if you're increasing internal energy, all things being equal, you might be increasing temperature. Okay, so that's how you can have a nozzle causing changes in temperature. And an even more extreme version of that, when we get to like throttling valves, well, that's what we saw when we had the refrigeration unit, right? We had temperature changes and things happening where you were getting well, I can't remember the numbers now. Anyway, we were using that though to cause the refrigerant to boil and things like that, right? So depending upon pressures and temperatures, you can drive various phase transitions using valves and things. Okay, so even though the enthalpy is constant, frequently you make that assumption that it's constant through a nozzle. That does not mean that nothing's happening. It just means that it means just what I said. Okay. All right. So turbine. All right. Now I'm going to go over here and hopefully I can download my images from Magic here. I love that. Maybe it'll work. Hope for the best. Oh, all right. Well, I'm not getting the best, but we'll just take a picture here and then I will drop it in. Apologize, it's not the image I wanted, but I'll use this one. Okay, so for whatever reason, the top of the image cut out. Can you guys see that at all? It's kind of, yeah, no? Yeah. All right, so up here, what this is supposed to be is you have a line going in and you have a larger. You have a line going in, you have these fan blades, they're spinning, and then you have the fluid flows through. You have you might, so what you want to do is you want to force the fluid to go through the fans, the turbine blades. You don't want to allow it to kind of leak around the edges, because it's kind of like it cheated. It didn't actually, it leaked around. If it leaks around the edges, then that's fluid flow that didn't actually push on the fan blades. That's fluid flow that doesn't produce work. And so there's a lot of engineering in how do you get the fan blades to be super close to the casing, the housing of the unit. But if these things are spinning fast, you can't let them touch, because then it breaks and destroys the whole thing. So there's a lot of engineering. So I don't want to. It's not just a fan, all right? Even though the physicist in me says, "Oh, it's just a fan." Well, no, there's a lot of tricky engineering in getting that right to get the clearances just to minimize that. So here is a situation where they say they've got a stationary blade. That's just kind of part of the housing. These don't move. And then you kind of have spinning blades in the middle. And the spinning blades are turning a shaft, a drive shaft, which, we'll learn about in physics too. You might, if you were to attach a magnet or something to those, then you can use a coil to make a generator, basically. That's what you could do. That'd be one way to extract power from this. Okay. Another sort of situation might be you have a water flow, so you have like a dam, right? So you arrange a situation where you have a water level on one side is high, water level on the other, and ultimately it's kind of maybe gravity even pulling it through. And as gravity pulls it through, you have a propeller blade, which gets spun, and you extract power from that. Okay, so you could do something like that. Right, so that's something like what we could be talking about. Now, if this was a dam driven by gravity, you're going to have potential energy in that case, right? But if we're talking about this kind of system, which is what we mostly are talking about, like at a power plant, or wow, we saw an example, at least on the board, where they had some sort of turbine in an ideal refrigeration cycle. In that case, there's no potential energy. There's no significant. Okay, oftentimes the fluid flow is big going in, and the fluid flow, the velocity is big going in, and maybe it's big going out. So you might think, oh, we should keep track of velocity. And maybe you have to. Just a second. Sorry. So the velocity is big going in, it's big going out. And you might think, oh, I should keep that. And maybe you should. But it's not the inputs or the outputs that really matter. Going back to our energy equation, our energy equation, right? It's, you have to, the inputs count as pluses, but the outputs count as losses. And it's really the difference in kinetic energies that would be important here. So if I'm looking at a flow like this, well, if the kinetic energies aren't significantly different on the inputs and outputs, then you would ignore kinetic energy. And that's very often going to be true. Okay. So a lot of times you'll just drop the kinetic energy change. Similarly, you'll want to minimize heat losses, as do the best you can. And a lot of times you will assume it's minimal. A lot of times the best you can do is going to be, remember, heat exchanges can be associated with entropy. So what you will do is assume that there's no specific entropy change, that at least in an ideal situation. So you'll assume that the specific entropy is constant throughout. Okay, so if I'm doing that, then my energy equation would become, kind of find my thing here, get my energy, my equation editor, is going to be oh, come on. It's supposed to show me my recent history here. History, show history. My energy equation then is just going to become so we're going to assume that there's only enthalpy and possibly a heat. So you'd have H in minus H exit. Sorry, it's taking a second to compile here. I think I lost the share here. Can you guys see this at all? I'm sorry. Can you see it now? All right. So if you, oh, what's wrong with this? Well, obviously, if you're talking about a turbine, you're going to have work. So I should put that in there. Sorry, forgot that component. Sorry, doing these equations like this looks better, but it's kind of clunky. Sorry. There we go. So the energy balance equation is going to say that you might have some heat loss. Oftentimes, numerically, though, sometimes that's negligible sometimes. Or instead of saying that that's zero, you might say that it's whatever it needs to be so that there's no change in entropy. And then the power extracted, right? If you're running a turbine, you're going to have work extracted, and then you have the change in enthalpy term. Okay, so that's going to be a standard kind of assumption for this. All right. Other questions about that? Does that make sense? All right. what I'm going to do is I'm going to give you a problem that I want you to work on. And take a couple seconds and let's kind of plan a route. And then between today and Wednesday, I want you to try to work it out on your own. All right. And then we're going to talk it through as a class. All right. But please try to do this. With us not meeting in person, it becomes more important that you kind of spend the time trying to work it out. In fact, what I think I may do is kind of let you guys go, but stay around to answer questions on it I want you to work this through. All right, so let me get the image from, hopefully it comes through. I hope this works. All right, I hope this is readable. All right, so I'm going to drop in an image, hopefully. So practice problem here. Full screen. This. It's not visible at all. Oh crap.
Not visible.
Give me 1 second. I'll resend it to myself, I guess. So frustrating. All right. Mail to me. See how that works. And then I'll go over to email. Sent. Download. Try this again. There you go. Okay, can you guys see that again? Can you see my screen? Yeah, can you read the problem now? Okay, all right. Okay, good. So what I want you to do is let's read through that and let's talk through a plan. And then I'm going to let you guys go and I want you to try to work on this. And I'm going to keep my Zoom meeting going. And try to do that. So steam enters a turbine operating at steady state with a mass flow rate of 4,600 kilograms per hour. So that's kilograms per hour. Okay, that's kind of, watch the units on that maybe. The turbine develops a power input of 1,000 kilowatts. Remember, kilowatts, that's energy per second. So that's why you got to watch that unit there. So 1,000 kilowatts. At the inlet, you're given a pressure and a temperature. 2 numbers for the input. That means you can look things up in the tables. And a velocity. At the exit, you're given a pressure and a quality. Again, 2 numbers. So you can find out things about the exit. And you're given a final velocity. Calculate the rate of heat transfer. So calculate Q dot. So if they ask you to calculate Q dot, that means you cannot assume that Q is 0, right? You got to calculate that. And the surroundings. So I got that in the wrong spot. Okay. All right. So let's kind of talk our way through this. What are the things we know? Or sorry, what do we want, first of all? We want Q dot. We know well, first of all, it's a turbine, so there's one input and one output. So that means that m dot is constant throughout. So it's just the same number throughout the whole problem. We also know that, let's see, what else do they tell us? And it's constant and it's given. We know power output. What quantity is that? So in this equation, what does power output mean? What symbol, what expression is power out? Which one of these would be power out?
So W.
W dot. If it's W, it's work. If it's W dot, it's power, work per second. So they're giving me W dot. These are knowns, right? W dot is known. And then I want Q dot. So I know these things. I know M dot. I want Q dot. So I need to find H in and H exit, right? In order to find Q dot, I need to find these. These are from the table, tables. So to do this, we need to have to look them up from the tables, you need to have two properties at each state before in the input and the output. Well, at each one of them, we have two properties. We know pressure in and temp in. We also know pressure out and quality out. So those are, so I can look up from the pressure in and temp in, I can get the enthalpy in and the enthalpy out. Now, there's one other thing. When I use this equation, is this equation the full equation, or have I made assumptions to get to this point? Tell me.
Made assumptions.
What assumptions, what did I drop to get to here?
Kinetic energy.
Exactly, that's the big one, and potential, but that's pretty standard. Okay, so let's go back to the full equation, or go back up here. There we go. The full equation had potential, drop that, but also we should have maybe kinetic energy. Now, oftentimes it doesn't matter, but since they gave me the velocities, it is implied that you should keep kinetic energies. So we're going to find kinetic energy in from velocity in and kinetic energy out from velocity out. Okay, a lot of times you don't need that, but because they gave you the information and literally it's just add in 1/2 mv or 1/2 v squared even, right? Because you don't do the math part, you should do it. Now, if you're keeping velocities, if you're keeping kinetic energy in there, you need to watch the units. You got to watch the units on those because they don't come out right, quote unquote. They come out in joules per second or joules per second, joules per kilogram per second. Whereas the other things come out in kilojoules. So you just got to watch that. Okay, and the key equation we're going to use then is this one. Let me copy it. Put it, oh, come on. Sorry. Copy. Why is it not? Do it this way. Sorry, give me one. There you go. Let me find it here. Yeah, these equations look better, but it's clunky as heck to get them typed and then transferred. Okay, so this is going to be our key equation. Can you guys see that? Can you give me a thumbs up if you're getting that? So it's the control volume equation. No, I forgot the work again. Son of a gun. It's because I'm copying and pasting from things. Give it a second. There we go. All right, so we've got there. We're trying to find the heat. They give us the work, enthalpy, and kinetic energy. That's got everything in it. Okay, so I'm going to let you guys. I'm officially letting you go. I'm going to stay around. So if you need help, call out. I'm helping kids, but I will export this to PDF. So if you don't have, if you want to, you can take a screenshot of this, but I will upload this file as a PDF, and you can work on it. Okay, and next time we'll kind of finish it off and then do more components to the systems. Everybody good? Do you understand what I want you to do? You give me a thumbs up? Yep. Okay. All right. Awesome. Tell you what I will do. While we're doing this, I will keep the problem visible on the screen to you, and you can work on it here and ask questions if you get stuck.
Since it gives us quality, does that mean we want to do it, take it like 90% of it is the saturated vapor and then 10% is the saturated liquid? So
Yes.
we just use that ratio of multiplying them?
Well, remember, you've got the formula for how do you look up properties for quality, using quality. So you look up the enthalpy of saturated vapor and the enthalpy of saturated liquid, and then you have to do X times the enthalpy of saturated vapor plus 1 minus X times the enthalpy of saturated liquid. I'll write that down. You're going to use H equals H saturated vapor times X plus H saturated liquid times 1 minus X. Is that okay, Billy?
X is just our quality though, right?
Where X is the quality. Yes.
Okay.
Does that answer your question?